Okay, afternoon everybody. What I'm going to give you today is a very brief overview of electrical engineering at Diamond and some of the techniques we use for controlling noise. Here's a very simplified view of the electrical systems in Diamond. We take in the power at 11,000 volts. We have a variety of transformers which bring it down to 400 volts, and there's a picture of them there. We break the supply up into various systems, magnets, dipole magnets, high power amplifiers, services on the end there, which is actually the majority of the power we use, and uninterruptible power supplies which feed the control systems for the magnets, diagnostics, etc., as you can see there. On the bottom left here, we have one of the storage ring electron beam position monitors. So on that picture, you've got megawatts at the top and microwatts at the bottom. The object of the exercise is for all these things to work together and not interfere. In terms of the precision we need, the magnet currents, which are measured in tens or hundreds of amperes, 1,000 amperes for the dipole supplies, and we monitor them with an 18-bit A to D. For those of you not familiar with binary arithmetic, that implies 1 part in 250,000. So, what's all this got to do with stability? Right, we need stable supplies from the national grid, obviously, keep us going. We need to protect sensitive equipment. That's what we use the uninterruptible supplies for. And we need to control noise within the electrical systems. Here I've got a picture of, it's actually a pressure control system for one of our superconducting undulators. The blue line, whoops, right. The blue line is, as you can see, it's hopping up and down a little bit to 2 millibar. That's the thing. The red line is the control to the heater, which keeps that pressure constant. And as you can see, that's wobbling up and down quite a lot. Now, that is effectively an image, an inverted image of the error in the control system. And some of that error comes from thermodynamic effects, some of it comes from electrical noise in the systems, and perhaps a little bit from a mechanical noise as well. So, I can't do much about the thermodynamics, I'm an electrical engineer, but I can do something about the electrics. So what do? We try and control the noise generated by electrical devices. We try and control the transmission of that noise to sensitive equipment, and we also like to make the sensitive equipment capable of tolerating a certain level of noise. Now that's a description of what's known as EMC, which is electromagnetic compatibility. The term EMC was invented by the EU, came out as a directive in the 1990s, and it says exactly those things. But if you're talking about a television or a washing machine, we put a CE mark on the back. Now, we know where to put a CE mark in Diamond, so we don't do that bit. But we do try and comply, so far as practical, with the requirements of the directive. So why did it become suddenly imperative in the 1990s that we do something when electrical engineers have been dealing with interference for 100 years, more than 100 years? The first recorded instance of it was by Victorian railway signal engineers when they found they were getting noise on their telegraph circuits. Well, the problem is the adoption of the switch mode power supply as the favoured means of changing voltages, or changing power, should I say. And here on the right is a super simplified diagram of a switch mode power supply. What we do is, rather than trying to vary the voltage to control a load, we simply rectify whatever incoming power we've got, 230 volts in this case, and then we chop it up. So instead of having 1 amp at 12 volts, we have a few milliamps at 300 volts, but only for a very short time. So we turn it off before it damages the load. There are, of course, filtering and control circuits in there I haven't shown. This results in interference. Now, it's the rapid change in current which causes the interference. And here's an oscillogram of the kind, typical of the kind of interference you get out of a switch mode power supply. That's the interference we're trying to control. Now, this technique has proved extremely powerful. It's a triumph of the semiconductor industry in the late 20th century that they actually managed to make these transistors which would withstand high voltages when they were off. They would pass very large currents when they were on with a very low resistance, and they would switch very rapidly. Absolutely great. So now when you buy your smartphone, it comes with a tiny little charger which is built into the plug. And it's because we use switch mode power supplies. We also use switch mode power supplies to drive the magnets in diamond up to 1 megawatt. So it's a universal technology. So what do we do about it? Right. There are a number of tried and tested methods of stopping that interference, either getting into sensitive equipment or getting out of interfering equipment. One of which is to put the signals, I don't know if you can quite see that, but those wires there are actually twisted pairs. So we use a lot of twisted pairs. You will also see there's a braid screen around that, copper braid. That copper braid is the screening element. It is connected to the metal shell of the connector there and the metal of the box there. So the box and the cable and the connector form a continuous screen. We can filter it. Here we have at the top is a motor drive unit, switch mode device again. Underneath it, we've got a large inductor. It's a 3-phase inductor in this case. What the inductor does is slows down the edges of those waveforms, which means we get less high frequencies generated, which doesn't radiate quite so well. We can also segregate cables. Here in this cable tray assembly along the side of a beam line, we have 1, 2, 3, 4 sets of cable management, 3 trays and cable duct. And the idea is that the heavily interfering stuff, at this end you can just see these orange cables, which drive motors, driven by motor drive units. And on the top, we have instrumentation cables going to those boxes at the top there. You'll notice there's also these copper bar on here and these braids. This is part of the earthing system, and this is one of the key ways we keep noise down in diamond. So, this is one of our main. This is an illustration from a description of the earthing system, and what it tells you is that everything is connected to everything else. All the extraneous metalwork. So we've got the walkway at the bottom, the cable trays, the structural steel. We also connect the reinforcing metal in the concrete storage ring. There's also lightning protection conductors and earth supplies that we bond into the system. The idea of this is to produce an earthing array with a very large surface area. That keeps the resistance down, and it reduces the ability of currents flowing in that to radiate energy, because the radiation from an antenna is proportional to the current density in its surface. So, what do we use? Well, conductivity is a key parameter for an earthing system. So copper's quite good. There is a problem, and it's skin depth. Alternating currents do not flow throughout the body of a conductor. They like to flow in the surface. And the depth is given by a formula, which is inversely proportional to inversely proportional to the frequency, the conductivity, and the magnetic permeability. So, we like that. That tells us copper's quite good. It's not magnetic. Steel, not a very good conductor, and when we take into account the magnetic permeability, it's even worse. However, we do use large surface areas. My apologies. Right. So the copper earthing bars are in the form of these tapes, and we've got lots of steel. It may not be a very good conductor, but we've got an awful lot of it, and connected together, it provides quite a good earthing plane. So, how effective has this been? Right. At the top there, we have a spectrum analyzer scan from above the storage ring. This is electric field we're looking at. And what you see is radio location and telemetry, broadcast TV, local telemetry and mobile phone at the top end. In the middle, you'll notice 500 megahertz is radiation from diamond. Now, I should point out that its level is a little bit more than minus 60 dBm, which actually corresponds to about 1 nanowatt. So there's not a huge amount of radio power. On the right there, we have a scan for the kilohertz range up to 100 kilohertz. And this blue bar in the middle indicates the sort of range where you'd expect to see the noise from switch mode power supplies. Well, there might be some there, but it's fairly well down in the noise. Most of this bit here is the noise floor of the spectrum analyzer. So, all right, might be a bit there, but it's fairly well suppressed. And just for completeness, on the bottom left hand, these two spikes here are at 100 and 150 hertz, second and third harmonic of the supply frequency. The interesting thing about our slide is we don't get 50 hertz, which means we've managed to balance the loads across the supply quite well. So all in all, we've done reasonably well at keeping the noise down in diamond. So that's it.
Thank you very much, Andrew. Any questions about electromagnetic noise?
So what is the concept that you follow for grounding your Earth mesh system to ground, really, to Earth? Is it star-like? Do you have several points where you connect your ground mesh to Earth, or what is the concept here?
There are hundreds of places where it goes to Earth. There's all the lightning protection points, which is every other vertical structural steel stanchion holding the building up. There's all the supply earth grounding mats, and there's a number of fortuitous things where we have external connections to earth, things like the foundations of storage tanks, which are all bonded down. So it's a very wide interconnection throughout under the whole of the diamond synchrotron.
Okay, it's another.
Hi. What level of harmonic distortion is there on the voltage to your incoming supply? Do you have a feel for that?
I'm trying to remember. I do have a feel for it, and I think we're looking at less than 20%.
And do you have a feel for any kind of current distortion that you're causing, imposing on that supply from the non-linear nature of your loads at Diamond?
I can't remember that one, but I do know it's less than the regulations allow. So probably not by much.
Okay, we've got time for another question if anyone's got one. No? Okay, let's thank Andrew. Thank you very much.